Great. So then I'll introduce the first speakers of today's QIP program. It is my great pleasure to introduce Laura Mančinska from the University of Copenhagen, who is going to explain us why quantum isomorphisms are equivalent to equality of homomorphism counts from planar graphs. So please, Laura.
Thanks, Angela. Good morning, everyone from sunny Copenhagen. So I want to tell you about this notion of quantum isomorphisms. And we're going to start in the world of quantum information and define these quantum isomorphisms as entanglement-assisted strategies for a certain non-local game. But then we're going to go on and see that the same notion of quantum isomorphism actually arises naturally from other areas of mathematics. Specifically, we're going to see that quantum isomorphisms can be reformulated in the language of quantum groups. Now, this is a non-commutative area of abstract mathematics. And also, we're going to see a combinatorial reformulation of these quantum isomorphisms. Before I go on, let me say a few words about my motivation and why I find this class of games interesting. Well, first, in general non-local games, we can see them as providing us with a systematic tool for studying entanglement and what advantage entanglement can bring in general in distributed scenarios. But there's one problem, namely that if you want to analyze entanglement-assisted strategies for an arbitrary non-local game, then they turn out to be somewhat unwieldy because they seem to lack some additional mathematical structure. Now, one way around this would be, instead of looking at a general non-local game, when you want to answer some question, you could look at some specific, better behaved class of games that does possess nice additional mathematical structure. And these quantum isomorphisms represent such class of games. All right, so roughly my talk will have two parts. In the first part, I'm going to introduce this notion of quantum isomorphism, and I will show you how we can look at them from these different perspectives. And in the second part, I'll try to give you some glimpse behind the scenes, sort of what goes into proving this combinatorial characterization of quantum isomorphism. All right. Graph isomorphism intuitively just captures this notion that two graphs are the same. Now, more formally, we need to speak about isomorphism map, and this is a bijection that takes the vertices of our first graph, G, to the vertices of the second graph, and this bijection preserves the structure of the graph. Namely, it preserves adjacency and non-adjacency. So here I'm using this tilde to denote adjacency. And whenever such a map exists, we're going to say that the two graphs are isomorphic, and I'm going to denote it using this congruence symbol. Now, there is another common way to think about and define graph isomorphism, and that is in terms of matrices. Specifically, the adjacency matrices of the two graphs, so this A sub G and A sub H. And now these are 0, 1 matrices whose rows and columns are indexed by the vertices of your graph. And then you place a 1 in the spot that corresponds to adjacent vertices. Now, in this setting, two graphs are isomorphic precisely when you can find a permutation matrix that conjugates the adjacency matrix of one graph to that of the other. Now, in order to talk about quantum isomorphism, we actually need yet another way to look at graph isomorphism. And this is going to be provided to us by a non-local game. For intuition, you can think that in this game, Alice and Bob are trying to convince a referee that two graphs are actually the same, that they are isomorphic. Now, how does this game go? So the verifier selects two vertices of graph G, sends one to Alice, another one to Bob. And the players need to respond with vertices from H. And the winning condition says that the answer vertices of H need to be related in the same way as the question vertices of G. Now, what do I mean by saying they need to be related in the same way? Well, if you take two vertices from some graph, then 1 out of 3 situations hold. Either it's actually the same vertex, these vertices are adjacent or they are distinct non-adjacent. Okay, so this relation takes 1 out of 3 different values, and it needs to match for the questions and answers for the 2 players to win. Now, as in any non-local game, there is no communication allowed between the players after they have received these questions. But of course, they know the 2 graphs G and H, and before the game starts, they could use this knowledge to agree on some strategy that they are going to use. Now, it's not too hard to show that the way we have constructed this game, that actually classical players, Alice and Bob, they can win precisely when the 2 graphs are the same. Okay, so for instance, one direction, if the graphs are the same, then you have this isomorphism map F. So both Alice and Bob could just respond with f of g and f of g prime respectively. Now, because that's F is an isomorphism map, all these conditions will be satisfied. All right, now this is something that we can prove in the case of classical strategies and graph isomorphism. Now we then take this as a point of departure and define quantum isomorphism as the ability of quantum players to win this isomorphism game with certainty. Okay, so when I say that 2 graphs are quantum isomorphic, I mean that there exists a quantum strategy that wins this game with certainty. And it's important to point out that I'm modeling here this composite Alice-Bob system using the so-called commuting model rather than the usual tensor product model. I'll discuss this a little bit more on the next slide. All right, so 2 graphs are quantum isomorphic precisely when there exists this quantum strategy for winning this game. Now, what does such a quantum strategy consist of? Well, it consists of 3 things: the state, the shared state, the measurements for Alice that she performs. So for every question that she can get, in this case, it's a vertex of our graph G, she has a measurement, and similarly for Bob. And then we can, without loss of generality, index the outcomes of the measurement that the players perform using the answer set. And in this case, those are vertices of H. Now, as I said, we are in this commuting model. So what is the mathematical description of these things? Well, this shared state is a unit vector in a Hilbert space that's not necessarily a tensor product space. Now, the measurements, the local measurements Alice and Bob perform, they are described by positive operators on this Hilbert space. And these operators for a fixed measurement, they need to add up to identity, just like in the usual case. But now the requirement that these measurements are local to Alice and Bob labs translates into the requirement that the measurement operators of Alice, each one of them commutes with each measurement operator of Bob. Okay, so rather than in the tensor product model, you would have for Alice E tensor identity on Bob's space and analogously for Bob. And of course, these operators would commute. Here, you're not imposing that tensor product structure, but you still require that they commute. Now, if we have a strategy of this form and the players use it in this game, then we can compute what's the probability that given questions G and G prime, Alice and Bob answer with H and H prime. And this is given by this inner product. Now, this should look very, very familiar, except that I don't have a tensor product here, but just a product of this E and F. All right, now this is a good point to mention that this quantum isomorphism is different from the classical notion. So there do exist pairs of graphs that are not isomorphic, but are nevertheless quantum isomorphic. And here is the smallest pair of such graphs that we are aware of. They have 24 vertices each. They have 24 vertices each, and we actually obtain these graphs from a general construction that is based on the reduction from the so-called linear constraint system games. And these particular graphs, they are obtained by reducing from the magic square game. So you can build the strategy from the strategy for magic square. The shared state, for instance, will just be 2 EPR pairs. And now this reduction actually allows us to obtain infinitely many examples of pairs of graphs that are not isomorphic, but are quantum isomorphic. Another consequence of this reduction is that it is undecidable to test quantum isomorphism. So given two graphs, it is undecidable to test whether they are quantum isomorphic. Another consequence is that actually this problem is complete for the complement of recursively enumerable languages and also for the zero gap variant of MIP star or MIP with commuting provers. All right. Next, I want to show you how we can reformulate quantum isomorphism in the language of quantum groups. To do this, I need to explain this notion of quantum permutation matrix. And this is something that is studied in this area of quantum groups. This is a generalization of a permutation matrix where you allow your matrix entries to not just be numbers, but you allow them to be elements from some C-star algebra. For instance, this could be the algebra of matrices. So now you have a matrix whose entries are matrices themselves. And you need two requirements. The first one is that your entries are projections. So they square to themselves and they are self-adjoint. And you need that along every column and along every row, your entries add up to 1, which is now the identity element in your C-star algebra. Okay. And if the C-star algebra was just complex numbers, in that case, you recover the notion of permutation matrix. This first requirement here, for instance, translates into saying that your entries are 0 and 1. And the second translates into saying that if I add them along any column or row, I get number 1. What we showed in our previous work is that quantum isomorphism is equivalent to there being a quantum permutation matrix which conjugates the adjacency matrix of the graph, one graph to that of the other. Now, if you remember the matrix formulation of isomorphism, you see that syntactically it looks exactly the same, except that now I allow the script P to be a quantum permutation matrix, which is a generalization. Right? So now if someone from the area of quantum groups wanted to define quantum isomorphism, it would be completely natural for them to take this matrix-based definition and replace this permutation matrix with now quantum permutation matrix. And it turns out that then they would, the notion they would arrive at, if this is the definition they started with, would be equivalent to our definition that we started with in terms of this non-local game. All right, so now that I have explained the relation to quantum groups, I want to go on to combinatorics. And in order to obtain a purely combinatorial characterization of quantum isomorphism, we will need graph homomorphisms. So graph homomorphism is an adjacency preserving mapping from the vertices of my graph F to the vertices of graph G. You need to preserve adjacency. You don't care here about non-adjacency. Only adjacency needs to be preserved. Here's an example. So for example, you can take 7 cycle and map it to the 5 cycle by identifying these 2 blue vertices and these 2 red vertices. And what you're doing, you're essentially folding these 3 edges here onto a single edge of your 5 cycle. Now, given 2 graphs, we might not only ask, is there a graph homomorphism from one to another, but we might want to ask how many graph homomorphisms are there? So we want to count them. And this number, I'm going to denote it by hom of F comma G. So the number of homomorphisms from F to G. There's a very nice result due to Lovasz, which says that these homomorphism counts actually determine a graph. So 2 graphs are the same precisely when they have the same number of homomorphisms from any graph F, okay? And now we were very surprised to find out that if instead of looking at all graphs, you only look at planar graphs. So you take this right-hand side in Lovasz's statement, and you only look at planar graphs, then the notion you arrive at is quantum isomorphism. Okay, so if you see this statement on the right-hand side, there's nothing about quantum mechanics, no non-local games, nothing like that. It turns out to be equivalent to this game definition of quantum isomorphism in terms of existence of perfect quantum strategy. And actually, this fits nicely within the larger context. So people have looked at the question of what happens if you look at counting homomorphisms from some fixed class of graphs, okay? So for instance, if you count the number of homomorphisms from all cycles and you require equality, then you recover this relation on graphs known as cospectrality. So adjacency matrices having the same eigenvalues. If you equality of homomorphism counts from all trees gives you this linear relaxation of a graph isomorphism known as fractional isomorphism, and even further relaxations of fractional isomorphisms that are known as K equivalents can be understood in terms of counting homomorphisms now from graphs of bounded tree width. Now, Dell, Grohe, and Rattan in this paper where they show these two relations, they also asked, oh, what happens if you are counting the number of homomorphisms from the class of planar graphs? And I don't think that they expected that the answer is going to be quantum homomorphisms. I don't think they knew what quantum homomorphism is. Quantum isomorphism is. And also they asked about the complexity. What's the complexity of testing equality of these homomorphism counts for the case of planar graphs? So let's first see for the other relations. If we look at the left-hand side, so testing isomorphism we know can be done in quasi-polynomial time. This fractional isomorphism and K equivalence, both of them can be tested in polynomial time. Right, so that implies that testing equality counts from these classes of graphs can be done in quasi-polynomial time and polynomial time respectively. Now things seem to be much more hard in the case if you look at testing homomorphism counts, equality of homomorphism counts from the class of planar graphs. Because we know that this testing quantum isomorphism is undecidable, so that means this right-hand side problem is also undecidable and also moreover complete for the complement of recursively enumerable languages. So now I want to tell you a few proof ingredients. So what goes into proving this equivalence of quantum isomorphism and counting these homomorphisms from planar graphs. And our starting point is a previous result where we have characterized quantum isomorphism in terms of what's known as quantum automorphism group of a graph. Unfortunately, I don't have enough time to go and explain the definition of this quantum automorphism group graph. And specifically, we look at the intertwiners of this quantum group. And what we do is we provide a combinatorial way to understand these intertwiners. Again, I'm not going to start from the first definition of intertwiners. What I'm going to use is a very nice characterization by Chassagnol of these intertwiners. So Chassagnol showed that all the intertwiners of the quantum automorphism group of G can be generated in the following manner. So we start with three matrices, U, M, and the adjacency matrix of the graph. And then we can apply, we can take their products whenever it's possible to multiply them together. We can take tensor products, and we can take complex conjugate transpose, and finally linear combinations. Now, what are these three elementary matrices? Well, U is just all ones vector of length n, where n is the number of vertices in your graph. And this matrix M is defined here in terms of action on standard basis vectors. So if you apply it on EI tensor EJ, it gives you EI if I and J are the same, and it gives you 0 if I is different from J. So this is a rectangular matrix, and this is a vector, and this is a square matrix. All right, but so to get our combinatorial characterization, we look at what's known as bilabeled graphs. Now, an LK bilabeled graph is a triple. So it consists of a graph together with an L tuple that I'm going to call the left tuple, and a K tuple, which I'm going to refer to as the right tuple. Right, so for instance, this is a bilabeled graph. So the underlying graph is K4, the complete graph with 4 vertices. And then the left tuple contains vertex 2, 1. The right tuple contains vertices 2, 2. Now I want to show you how we can draw these bilabeled graphs. Well, the graph part, we know how to draw. So we draw the graph first. And then we indicate these left tuple, vertices in the left tuple and right tuple using what I'm going to call wires. Okay, so each of the wires is going to correspond to one vertex, and the wires on the left-hand side correspond to vertices in the left tuple, and similarly for the right one. So what I do is I put my wire, all my left wires start on the very left-hand side of the diagram, and the top wire goes to the first vertex in the left tuple, so 2, and then next one, second one, goes to the second vertex in my left tuple, so 1. In my right tuple, I have 2, 2, so both of my wires go to vertex number 2. All right, now here I have drawn 3 more examples of bilabeled graphs, which I have suggestively named U arrow, M arrow, and A arrow. For all 3, so in the first 2 cases, the underlying graph is just 1 vertex, so K1. And in this last one, the underlying graph is K2. Okay, so these are bilabeled graphs, but remember these intertwiners, they are matrices. So I need to somehow get to matrices. And the way we do it is via these, what we call homomorphism counting matrices. I'm going to explain it on a 1-1 bilabeled graph for simplicity. So suppose we have a graph G, and then we have bilabeled graph F with 1 left vertex and 1 right vertex. Then the homomorphism counting matrix of this bilabeled graph F is a matrix whose rows and columns are indexed by vertices of G. And in the UV entry, I write the number of homomorphisms from F to G that send this vertex A to U and this vertex B to V. So what I've done here is I've taken the number of all homomorphisms from F to G, and I've partitioned them according to the image of vertex A and B. So if I added all the numbers up, I will get the number of homomorphisms from F to G. So here's an example of homomorphism counting matrix for this bilabeled graph A. So let's see, in the UV entry, I need to put the number of homomorphisms that take vertex 1 to U and 2 to V. Now, because it's a graph homomorphism, there only is going to, if vertices U and V are not adjacent, then there's not going to be, because 1 and 2 are adjacent, I need to map them to adjacent vertices, then there are going to be 0 such graph homomorphisms if U and V are not adjacent. And now if they are adjacent, there's precisely 1 homomorphism. Well, because by specifying where 1 and 2 go, I've specified where all the vertices in my graph go, because there are only 2. Okay, so what we see here is that I've gotten this matrix, right? So I have a 1 precisely when the 2 vertices of G are adjacent. And this is nothing else but the adjacency matrix of my graph. So the homomorphism counting matrix for this A arrow is the adjacency matrix of the graph. And similarly, we can show that the homomorphism counting matrices of U arrow is U, and similarly for M. Okay, so now what we have is we have a combinatorial characterization of these 3 starting matrices in Chassagnol's characterization of intertwiners. So what I need to understand next is what is the graph operation that corresponds to these matrix operations of matrix multiplication, tensor product, and conjugate transpose. Here I'm only going to show you matrix product. So it turns out that if you take the product of the 2 homomorphism counting matrices, then this corresponds to the homomorphism counting matrix for the bilabeled graph that you obtain by performing this operation. What does this operation do? Well, you draw your 2 graphs, F1 and F2, next to each other. because you can multiply these matrices together, that means that their dimensions match, which means that the number of right arrows of F1 is equal to the number of left arrows of F2. So you can think of joining these wires together. And then you contract them, and this will end up identifying some of the vertices. And this, then that is the resulting bilabeled graph that you obtain. And you can similarly get characterizations for this tensor product and conjugate transpose as well. So now what we have is we have understanding in terms of graphs of these starting intertwiners, simple matrices, and also of these operations. So in order to understand the set of all intertwiners, we should then understand what is the class of graphs that we can get by starting with these three small bilabeled graphs and then performing these graph operations. And it turns out that what you get is this class of what we call planar bilabeled graphs. These starting graphs are all planar, and these operations preserve this planarity. If I want to define precisely these planar bilabeled graphs, I have to be a little bit careful, but intuitively what it means is that the graph itself is planar, but also if you draw these wires, then this whole drawing is still planar. So you can do it without any crossings of wires or edges. All right, so what this tells you, finally, this is how these planar graphs arise, and it tells you that these intertwiners are simply given by the linear span of homomorphism counting matrices of planar bilabeled graphs. All right, so since I have only a few minutes left, I will just stop here and leave a few minutes for questions.
Great, so thank you so much for the very nice talk, Laura. It was super interesting. It seems there are a lot of questions on Slack, you will see later, but at least your co-author and some other participants were kind enough to answer most of them. So I will just pick some of them to ask to you quickly. So for example, Harold Newboer is asking, do you know of any planar graphs G and H which are quantum isomorphic but not normal isomorphic?
Do we know planar graphs? Good question. I'm afraid I cannot I cannot say on top of my head. I mean, in general, right, this problem of testing is hard. So there's only, I don't think we have a good understanding of precisely which graphs are quantum isomorphic. We have families of examples of such pairs.
Great, thanks. So it seems that your talk has raised a very interesting discussion on Slack, but I'm afraid that for the interest of time, we will have to move it to the round table after all the talks of this morning session. Right. So Laura will be joining you in this round table at 12:30. So please feel free to keep asking her all your questions there. And thank you very much, Laura, again for your talk.
Thank you, everyone.